Hi students, this is the video for tutorial number 1 for network simulation course. We are going to discuss some important terms we have discussed in first lecture, random number generators. Every simulation program has to have its own random number generator. Based on the simulation program, if it's based on C, C++, or Java, each of these programming languages has its own random number generators. In this tutorial, we will understand how random number is generated. It's not easy, and there is no specific rule to generate a random number that is quite random by itself. It has to have some equation or some limited thing. We will discuss why it's important to produce random numbers in simulation. A simulation of any system or process in which there are inherently random components requires a method of generating or obtaining numbers that are random in some sense. A good arithmetic random generator should be possesses several properties. The first property is, above all, the numbers produced should appear to be distributed uniformly between 0 and 1 and should not exhibit any correlation with each other. It means that the two random numbers generated by a system they should have zero correlation among them. Okay. Otherwise, the simulation results may be completely invalid. The second point is, from a practical standpoint, we would naturally like the generator to be fast and avoid the need of lots of storage. Okay. Since you are dealing with a simulation that may take some time, takes long times in simulations, you don't have to make it more complicated by generating random variables that last time by itself. So your random number generator should be simple and good. Number 3, we would like to be able to reproduce a given stream of random exactly for at least 2 reasons. First, this can sometimes make debugging or verification of computer program easier. Second, we may want to use identical random numbers in simulating different systems in order to obtain a more precise comparison. So, for example, if you are going to simulate a simple program and you have some mistake in the coding or something or lag, and to rerun the simulation, you have to have the same stream of random numbers just to check if your program is doing well or doesn't have error. Sometimes if these streams of numbers are not exactly, your simulation will be run fine for the first time, and if you run it again, it will fail to run. So we would like to have a good stream of random numbers. We can use it many times. Also, if you are going to test the system twice or for different conditions, you may have the same output for it. Okay, number 4, there should be provision in the generator for easily producing separate streams of random numbers. So if you want to change the streams, you have to have this option as well. We would like the generator to be portable, i.e. to produce same sequence of random variables at least to the machine accuracy for all standard compilers or computers. For example, if 2 students are running the same simulator in 2 different laptops, each laptop has its own specification, they should get the same results, because this does not mean that your generator will be computer specific. Your generator should be portable. Like if you run your random number generator in this computer and another computer on your cell phone, they should produce the same sequence of random numbers. Okay, there are many actually random number generators. In this tutorial, we are focused on one simple one, which many computer systems they use today. Many random generators in use today are using linear congressional generator (LCGs). They were used by Lamar in 1951, a sequence of integers z1, z2 defined by recursive formula. You may be very familiar with this equation in your logic circuit. course, you all studied the pseudo-random generator by using XOR. The XOR in this term, in this equation, is the mode, actually. So we have how many parameters? Z, Zi, and we have A, we have Zi minus 1, previous value of Z, and we have C, constant C, and we have M, the modulus of your system, where M is the modulus, A is the multiplier, and C is the increment. As you see from this equation, it's a linear equation, simple linear first degree equation. For this reason, they call it linear congressional generator. Z naught, the first Z you are going to use here, they call it Z naught, is going to be the seed. Usually they are non-negative integers. To obtain Zi, we will divide A, Z, for the previous one, for the first time is Z naught, which is Z, and added by C, and then divided by M, to let Zi be the remainder of this division. So the next Zi will be the modulus for this reason. To obtain the desired number of variables UI, the UI is the sequence we are talking about, the stream of random variables for 1, 2, 3, etc. Based on 0, 1, we will let to UI to Zi divided by M. For normalization progress, because we all need random numbers to be generated between 0 and 1, these randoms are more than 0 or greater than 1, so what you get is to divide Zi by M. You know that M is the maximum number you get from the generator. So if you divide any results of measures by M, it will be between 0 and 1. Okay. To make sure that LCG has full period, the following theorem should be applied to choosing in parameters. Okay. So you are not free to use these parameters A, C, M. There are specific rules to make your linear congruential generator to perform good as a good random number generator. We have 3 rules for this LCG to be valid. The only positive integer that exactly divides both M and C is 1. So this means that C and M should be its LCG or its GCD. You may not study GCD before, because usually we study this in modern algebra. Neglect the GCD. So if you can, there is no common factor between M and C except 1. The best way to use these numbers, to choose such numbers, is to use both prime numbers C and M. If they are both prime numbers, then their common division is 1. If a Q is a prime number divisible by only itself and 1, that divides M, then Q divides A minus 2. This is a very good condition. A minus 1, sorry. If 4 divides M, then 4 divides A minus 1. If you follow these 3 conditions in choosing A, C, and M, then you are good to go with your LCG. Let's have an example here. Consider the following LCG. M is 16. Look, this is not a prime number, and A is 5. Because A is a prime number, so by default, not by default, sorry, M and A they don't divide each other. So the most greatest common factor divisor for M and 5 A is 1 itself. Okay, so the first condition passed. The only positive integer that exactly divides both M and C is 1. Okay. The second condition is that if Q is a prime number divisible by only itself and 1 that divides M, then Q divides A minus 1. So to have a prime number that divides 16, it should also divide, sorry, for the first condition we said M and C, not A. C also is a 3, so a 3 is not divisible by 16 by any means. So M and C is the first condition. For the second condition, we have A minus 1, which is 4. So the prime number that divides 16 and 4 is 2. Okay, so the second condition is also valid. The Q is the prime number, 2 is a prime number. It divides M and also divides A minus 1. Okay, for the next condition, if 4 divides M, then 4 divides A minus 1. This is also valid. We have here 4, we can divide M by 4, then A also divided by 4, A minus 1 divided by 4 also. So the third condition is valid. Then these numbers are okay. We are good to go with that. We are with our random number generator. So one student may ask us, what if I have choose these numbers randomly? Look what will happen. Since we have 16 is the maximum number of random stream numbers, so we will get, look for this, if you apply this equation, for the seed, we choose 7. You can arbitrarily choose any number between 1 and 16 and 15, sorry. That should be less than M. For the first iteration, we don't have EUI. For the first number 1, we have 6. If we divide 6 by, remember the law, if we divide 6 by what? By M, 16, you will get this random number. For the second one, you have this random number, and so on. Look, there is no any repetition. 6, 7, 1, 8, 11, 10, 5, 12. The only repetition will occur after we pass the number 16, which is the number of possible random numbers we will have. Okay, this means our test is for this LCG has passed, because there has been no repetition between UI we received for the last 16 items. So obviously these random numbers, they have zero correlation among them, so they are good to use in our simulation. Okay, in real computer system we don't use simple numbers. If you expand M by many digits, you will have almost like as many as you want random numbers to get from this, unless if you follow these rules. Okay. Random number generators is not easy. All random number generators currently used in computer simulators are actually completely deterministic. It means that you will, like if you know your UI is 0.375, you will, if you know the equation, then you will know the next UI 06. So this means that these numbers are deterministic. Okay, there is something called testing random number generators. There are many laws and many equations to test your system random number. We are not going to deal with it because it's out of the scope of this course, and it has deep mathematics you have to understand. I'm pretty sure you haven't studied modern algebra, so we will skip this. But you have to know that if you are going to generate a good random number, then you have to test it by these tests. There are methods from the literature. If you are curious about it, you can read the second textbook, chapter number 7, for testing your number generator. Thank you.